All right, so here's the video for the Unit 9 practice tests. So the first question is asking about whether we can reject a null hypothesis in favor of alternative at a 1% level, if we can reject it at a 5% level. So if we're saying a 5% level, that's alpha of 0.05. If we're rejecting at that level, then that means we know that our p-value is less than 0.05. So it's asking if we reduce our alpha level to 0.01, what can we say? Oops, 0.01. What can we say? Well, rejecting at the 0.05 level would just mean that our p-value can be anywhere less than that. So it could be 0.04. If it were 0.04, we wouldn't be able to reject at 0.01, but we would also reject at a 0.05 level if our p-value was like 0.001, which would also be less than 0.01. So since we don't know what our p-value is, we say that the answer cannot be determined from the information given. All right, so question 2 says we have a null and alternative hypothesis. We have a sample size of 80, and we have a test statistic z equals 0.8. Find the p-value. So since this is z, we're going to look at our normal distribution, which is right here. And since our HA says not equal to, that means that we're going to do this symbol right here, so the two-tailed test, and our test statistic is 0.8. So that means we're going to look at negative 0.8 and positive 0.8. So that's getting me a test statistic of 0.4237. So 0.4237, the closest one is going to be D. All right, the second one, we still have an HA of not equal to. It gives me a test statistic of Z equals negative 2.4. So we're going to do it the exact same way. So negative 2.4, so it's two-tailed again. Negative 2.4 and positive 2.4. That gives me a test statistic of 0.0164. So 0.0164. So the closest one is going to be D, 0.016. All right, question 4 is we're looking for the correct interpretation of a type 2 error. So type 2 error is when you fail to reject the null, but the alternative is true. So that's like this is a false negative, which means that you're going to conclude that the suspect is innocent, but they're actually guilty. So conclude that the suspect is innocent when he or she really isn't. So that would be the correct interpretation of a type 2 error. That is a false negative. We think that they're innocent, but they really aren't. All right, question number 5 is another p-value question. Our alternative hypothesis is a greater than symbol, and we have a test statistic of 2.45. So we're going to choose greater than, and we're going to do 2.45. That gives me a p-value of 0.0071. So that's going to be B. All right. Question number 6. In this case, we're basically trying to determine what decision that we're going to make based off the p-value. So let's see. We're given x bar. We're given mu. We're given the standard deviation. We have n. So first thing we're going to have to do is we're going to have to find our test statistic. Well, since our sample size is less than 30, we know that we're going to be using t. And to find t, it's going to be x bar minus mu, so 13.82 minus 14 over s, 0.24, over the square root of n, which is going to be 16. So we're going to type that in. So 13.82 minus 14 over 0.24 over the square root of 16. We get a test statistic of negative 3. And for our degrees of freedom, it's going to be n minus 1, so 16 minus 1, which is 15. So since we're using t, we know we need to use our student t distribution. So I'm going to change that here. Our degrees of freedom is going to be 15. And then since HA says less than 14, we're going to choose less than, and we're going to type in -3. So that gives me a p-value of 0.0045, which is very, very small. Oops. So since our p-value is 0.0045, that means that we can reject our null hypothesis basically at the lowest level, 0.01. Okay. So then 17, we're describing a type 1 error. So type 1 error is a false positive, meaning we think we found something, but we really didn't. So we think we determined that they're underfilling the bags, but they really aren't. So we're concluding that the bags are being underfilled when they actually aren't. So that would be A. That would be the correct interpretation of a type 1 error. All right, the next question is question number 8. So it says a random sample of 100 voters produced 59 voters in favor of candidate A. Observed value of the test statistic for testing the null hypothesis is p equals 0.5 versus the alternative p is greater than 0.5. So we want to find the test statistic. So first thing we need to do is determine if we're using Z or T. So in this particular problem, since we're dealing with proportions, we know that we have to be using Z. So I'm going to cross out C and D since those are both T. So now we need to figure out which one it is. So if we look at this, the only difference between the two is what's in the denominator here. So this one is 0.59 times 0.41, and this is 0.5 times 0.5. Well, remember the only place where you use p hat, so p hat in this case is going to be 59 divided by 100. That's proportion in the sample. That's going to be 0.59. The only place where you use p hat is in this place here. In the denominator, this should be p times 1 minus p. So in this problem, since A, this is 0.59 times 0.41, that's p hat times 1 minus p hat. This isn't going to be the correct option. This would be the correct test statistic. It's p hat, so correct formula would be p hat minus p over the square root of p times 1 minus p over n, which this would be the correct numbers for that one. All right, question number 9. So it gives us some information about testing batches of the soy compound, and it's asking what is the appropriate statistical hypotheses and the observed value of the corresponding test statistic. So if we look, let's first look at the hypotheses here. They are hoping to prove that the soybean compound has more protein, so that means that we should be using a greater than symbol in our HA. So if we look at the HA, the greater than symbol is either going to be option B or C, because those both have greater than. So now we need to figure out the only difference between these two is Z versus T. Z versus T. So if we look, our sample size is 5. Anytime your sample size is less than 30, we should be using T. So the correct option is going to be B. So there's actually no calculation that you actually need to do here, since the only differences between the options is Z versus T, and here greater than versus less than. All right. So looking at number 10. So number 10, this is just choosing the correct appropriate null and alternative hypotheses. We're comparing two groups. We're comparing the excellent versus the simple brand for the aspirin tablets. And it tells us that we're trying to see if excellent aspirin cures headaches significantly faster, which we say is in less time than simple's aspirin. So less time means that we should be using a less than symbol. So we want excellent to be less than simple. So if we look here, we know that our HO should always have an equal sign, which means that we should be able to eliminate D and E. And then if we look at these ones, we're looking for excellent to be less than simple. So that's going to be option C. This would mean that the mean time that they cure the headaches is less than the mean time that simple uses to cure headaches. Okay. Question number 11. It's asking if employees are equally prone to having accidents. We're investigating the hypotheses. So they give us data. So this is where we're comparing two categorical data. So this is going to be chi-square test of association, notes 9-8. And it's asking us to find the expected number of employees under the age of 25 who had a burn. So under the age of 25 who had a burn, we're looking for the expected count for this particular cell. So remember the expected count, we do row total times the column total divided by n. So our row total, we're going to do 9 plus 17 plus 5, which I can't do that on my head. So 9 plus 17 plus 5 is 31. So it's going to be 31 times our column total. Well, 17 plus 13, that's 30. And then our total, so I'm going to add these all together, 17 plus 5 plus 61 plus 13 plus 12. And in this case is going to be 117. So that's going to be divided by 117. So we're going to do 31 times 30 over 117, and that's going to be give me my expected count. So let's see. So 31 times 30 divided by 117 gives me 7.95. So the closest answer is going to be C. All right, now we're looking at question number 12. So it says it's the same question as the previous problem, but now it's telling us that they give us a test statistic and they give us a p-value. We want to know which of the following statements is correct. So A is we cannot proceed with inference because 2 of the entries are less than 5. So remember, well, first of all, 2 of the entries are not less than 5. And remember, that's only with the expected count. So if you actually do the expected counts, none of the expected counts are less than 5. So it cannot be A. It says the purpose of the study to see if accident types depends on gender. Well, we are looking at accident types, but the other variable is not gender, it's age. So that's not going to be B. The number of degrees of freedom is 6 minus 1 is equal to 5. For the chi-square test of association, remember that the degrees of freedom is row minus 1 times column minus 1. So that's not how we do the degrees of freedom. According to the central limit theorem, sample size is large enough to permit the use of the normal distribution. Remember, with this type of test, we do not use a normal distribution. We use a chi-square distribution, so it's not going to be D. So it looks like E is the answer, but let's read it to make sure. Small p-value tells us there's evidence of a strong association between age and type of accident. So that is the correct conclusion you would make from the p-value. Remember, HO would be that there's no association between the two variables. HA that there is an association between the two variables. So since our p-value is low, we reject our null and conclude that there is an association between the two variables. All right, question number 13. So here's a free response question. We're doing a significance test. We want to see if the mean IQ score at this school is above average, and we're going to use an alpha of 0.05. So let's first identify our symbols in this case. So mu is going to be 100. That's our average IQ. They give us sigma in this problem is 15. They give us 30 students, so n is equal to 30. And they give us the mean of our sample. So 108 is going to be x bar. Okay, so our hypothesis, this problem is about means. So it's going to be mu is equal to 100. And HA, we want to know if it's above average. So we want to know if mu is greater than 100, where mu is the average IQ score of students at the school. Okay, so now let's check our conditions. So for the independent condition, n is going to be all students at the school is greater than or equal to 300. That's reasonable to assume. For the normal condition, in this case, 30, it just has to be greater than or equal to 30, which it is, which means our distribution is approximately normal. And then for the random condition, let's see, it does say a random sample, so that was stated. All right, so now let's go into our test statistic. So with means, we need to figure out if we're using Z versus T. So in this case, our sample size is 30, so that's good. And we know sigma. So in that case, we actually are going to use Z for this particular problem. So it's going to be x bar minus the mean, so 108 minus 100 over sigma over the square root of n, so square root of 30. So 108 minus 100 over 15 over the square root of 30. That gives me a test statistic of 2.92. So now we want to find, since we're looking for greater than 2.92, since we're using z, that means we're going to use our normal distribution. And we're going to choose greater than, and it's going to be 2.92. So that gives me a p-value of 0.0018. So the interpretation in context, I'm just going to say it verbally instead of writing it. I'm going to say, since our p-value is 0.0018 is less than alpha of 0.05, we reject HO. We conclude that the mean IQ score of students at this school is greater than 100, or you can say is above average. Great. So B, again, I'm just going to do this verbally. Type 1 error in the context of this problem, a type 1 error would be a false positive, meaning you conclude that the IQ scores are greater than 100, but they're actually equal to 100. That would be a type 1 error. And then question C says to describe a type 2 error. So a type 2 error would be just the opposite. It would be a false negative. You conclude that it's equal to 100, the mean IQ is equal to 100, but it's actually greater than 100. All right, question number 14. It says the utility claims that 80% of his customers are very satisfied with the service. Newspaper thinks that the percent of satisfied customers is less than 80%. To test this claim, they survey 100 customers using simple random sampling. Among the sample customers, 78 say they are very satisfied. Based on the sample, is there support for the newspaper's claim that the proportion of satisfied customers is less than 0.8? So in this problem, we are doing a test of proportions, and it's a one sample test. So first, let's identify our symbols. So P represents the population proportion. That's what the utility is claiming. That's 80%, so that's going to be 0.80. P hat is the proportion of the sample that say they're satisfied. So in that case, they said 78 out of 100. So 78 divided by 100 is 0.78. And then our sample size is going to be 100. So now let's do our null alternative hypotheses. So HO is going to be that P equals 0.80. HA is what the newspaper is trying to claim, that it's less than 80%, where P represents a proportion of satisfied customers. All right, so now let's check our condition. So the independent condition, big N in this case is going to be all customers. That's greater than or equal to 1,000. That's reasonable to assume. The normal condition, so remember the normal condition, we do N times P. So basically saying, like, in a perfect world, if what the company was claiming was true, how many people would say that they were satisfied? So N times P, 100 times 0.8, that's 80, which is greater than 10, so that's good. And remember, we do 100 times 1 minus P. That's going to be 20. That's also greater than 10, so that's good, which means our distribution is approximately normal. And then the random condition, it does say simple random sample, so SRS is stated. So our conditions are met. All right, so now let's find our test statistic. So with proportions, remember that we're always using Z. So it's going to be P hat minus P, so it's going to be 0.78 minus 0.8 over the square root of P times 1 minus P over N. So 0.78 minus 0.80. So 0.8 times 1 minus 0.8 over n. So our test statistic is going to be negative 0.5. So to find the p-value, since HA says less than, we're looking for less than negative 0.5. So normal distribution, since it's z, we're looking for less than negative 0.5, so 0.3085. So since that is greater than alpha of 0.05, we're going to fail to reject our null hypothesis. So again, I'm going to do my conclusion just verbally. I'm not going to write it down. We're going to say since our p-value 0.3085 is greater than alpha of 0.05, we fail to reject HO. We do not have convincing evidence that the proportion of satisfied customers is less than 80%. All right, so now let's look at the very last problem here. So accident records at the large engineering company in England reported the following number of injuries on each shift for 1 year. They want to know if there's good evidence that the injuries are not equally probable at different times of the day. So we're going to do a hypothesis test. So this is going to be the chi-square test of goodness of fit because we have one categorical variable, which is what shift it is, and we want to know if it's not equally probable. Okay, so starting with our null hypothesis. Our null hypothesis is that injuries are equally probable. At different times, which means that HA is just going to be the opposite, that injuries are not equally probable. Okay. For the conditions, before we do the conditions, we do need to do the expected counts. So this expected counts is fairly straightforward because there's only 3 categories, and if they were equally probable, we would have the same number in each thing. So first thing we need to do is we need to figure out how many total number of injuries. So I'm going to add these 1372 plus 1578 plus 1686. That's going to be 4,636. So my expected counts, we're just going to divide this number, sorry, it's blurry, divide this number by 3. So 4636 divided by 3 is 1545.33. So if our null hypothesis were true for the expected counts, we'd have the same amount of injuries in each category. So now we can go ahead and do our conditions. So the independent condition is the same. So big N would be all injuries. It's greater than or equal to 46360. That is reasonable. If you just think all injuries over time, that's reasonable to assume. In this case, the conditions for the chi-square test of goodness of fit, it's that the expected counts are all greater than 5, which they all are. All expected counts are greater than 5, so that condition is met. And then we do need to say random. Let's see. So actually in this problem it doesn't state it, but for the sake of just completing the problem, we're just going to say random was met. Okay, so now let's go ahead and do the calculation. So we do have included our table of expected counts. That's right here. So now we're going to do our calculations. So remember, with the chi-square test of goodness of fit, the chi-square test statistic is going to be the observed minus the expected squared divided by the expected. So it's going to be 1372 minus 1545.33 squared over the expected, 1545.33. And we're going to do that for each category here. So it's going to be, the next one's going to be 1578 minus 1545.33 squared over 1545.33. And then the last one, 1686 minus 1545.33 squared over 1545.33. And that's going to give me my chi-square. That's going to give me my chi-square test statistic. So it's going to be kind of a pain to type in, but we can do it. So 1372 minus 1545.33 squared over 1545.33. So actually what's nice about the Desmos calculators, you can just copy and paste. And since the expected counts are all the same, all we have to change is this observed count. So 1578 is the next one. And then lastly, 1686. All right, so my test statistic is going to be 32, we'll say 32.94. So that's my test statistic. For degrees of freedom, it's number of categories minus 1. So there's 3 categories. So 3 minus 1 is going to be 2. So now let's get our p-value. So we're going to use the chi-square calculator. Remember, we always choose greater than for the chi-square calculator. Degrees of freedom is 2. And then our test statistic is 32.94. So that gives me a p-value of basically 0. So it's really, 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 really small since that test statistic is pretty big. So p-value is basically equal to 0. All right, so our conclusions. P-value is really small, so we're going to reject our null hypothesis. So you would say since our p-value 0 is less than alpha of 0.05, we reject HO. We have convincing evidence that injuries are not equally probable at different times of the day.